Hello everyone, my name is Abdelrahman, and today I'm going to present the paper for low rank adaptation of swim transformers for skin cancer diagnosis. So first of all, as an introduction, what is this paper about? It's about introducing LoRa, which is a parameter efficient fine-tuning method for adapting swim transformer for the skin cancer diagnosis task. So the task is basically classifying 7 skin lesion classes, which is from the HAM1000 datasets, and it's a known dataset for the skin cancer. And the result is basically it reduces the number of tunable parameters by 68%, which is giving higher accuracy for the model itself. So if we are going to talk about a very high overview for the method itself, we have the backbone as a swim transformer, and we add some LoRa adapters to it. We take the pictures from the skin cancer dataset, and we get a classification for it. So what is the motivation for this? First of all, skin cancer is the most common cancer. Early detection saves a lot of lives, so it is a very crucial task. Second, vision transformers reach a state-of-the-art performance, but it needs very costly GPUs. You cannot run it on a single GPU if you will do full fine-tuning for the model. So that's why they use LoRa for enabling a single GPU training for the model. So for some background about the pre-training and what is parameter efficient fine-tuning. So foundation models in general learn genomic features from very high datasets, like for example ImageNet or some large datasets which contain plenty of data points. We have some foundation models. These foundation models learn their knowledge or pre-trained knowledge from these high-scale datasets. Then we can use these foundation models to tailor it to some downstream task, which we can use, such as the skin cancer task. So full fine-tuning on a small data set, especially in the medical field, can cause overfitting, because we have the data set is very small, and most usually it's very high quality data, labeled data, but in the inference time, this high quality data, there's a distribution gap between the data that the model was trained on and the data that the model will use during the inference time. So that's why we use PEFT, which stands for parameter efficient fine-tuning. It has some methods such as LoRa, adapters, any other methods. And the advantage of this, it can update only 5% of the weight, and the 5% of this weight can achieve rapid specialization. We can take the models, the pre-trained knowledge with its pre-trained knowledge, and transfer it to a very specific task, such as classifying the skin cancer disease dataset that we have. So as we can see here, we have the pre-trained vision transformer. We can apply to it one of the adapters we have, and we can get it to achieve several tasks. It can be, as we have in this paper, a dermo classifier, which used to classify a dermatology dataset, which is a HAM1000. Or it can, for example, used for some other tasks such as the chest X-ray or pathology task or any other medical task. So the key concepts we have here is, first of all, the swim transformer. The swim transformer, it's a fundamental transformer type that has arose in 2021. It's basically a hierarchical vision transformer with shifted window attention. So basically, the shifted window attention, or we can think of attention in a very general manner, is something that helps the model itself to catch the features, to learn more about the features. It can help the model to capture both the local and the global features. So using this attention, the model can learn what features in the image or the dataset it can use to do correct classification, and what other features it can focus less on to get a more robust classification and higher accuracy. And LoRa, as we see, we have basically the model, if we treated it as a black box, it is basically some of matrices. Like basically you get the image, you embed to the model, some matrices multiplication happen, and you get the output that you need. So what LoRa does, we freeze all the weights of the model, all the matrices, we don't update them, we don't change them, and we just add a multiplication of 2 low-rank matrices. These matrices is very small, it's not very large compared to the original weight models, and we just update these small weights or small matrices such that these matrices will capture the needed changes to the pre-trained knowledge or the pre-trained weights we have for the model to adapt it to the needed task. So what is new in this paper? This paper is a short paper accepted in middle 2025. It's a medical imaging conference. And this paper is the first LoRa SWIN study in dermatology imaging. It's basically the first kind of paper that merges like SWIN transformer used for classification with LoRa adapters. And it takes roughly 2 hours of training on RTX 3090, which is 24 gigabyte GPU. The advantage of this is that this GPU it's single GPU. The training time is not very high, and it's affordable. It's not like a very high end or a very expensive cluster. Also, the code released, and they are saying that we can take this code or the code they have done, and we can apply to any VIT or visual transformer backbone to get a similar results. So if we imagine here that we have the SWIN transformers blocks as our backbone, we add here the small blocks which is for the LoRa adapters, and then we get finally on the single GPU we can get our model running to do the classification for us. So roughly talking about the methods, we have the data which is 1,000 data set. We have it with 10K images, 7 classes, and we have the training using the Adam optimizer with a learning rate of 10 power -4 with a cosine decay learning scheduler, and we have the augmentation using flips and rotation and many other things to apply augmentations or variations to the data so the model can generalize well. So as we can see here in the results, we have the accuracy. We start with a baseline, is the original SWIN transformer, which is our original backbone. They computed or done inference to it on the original dataset, and they got the performance or the accuracy to be 85.7 on the original SWIN transformer. When they adapted or added the LoRa parameters, we pushed the performance to reach 87.4, and then while we increase the rank of the adapter or the rank of the small matrices that we add or the size of these matrices, we can see that the performance is getting lower, which indicates that we have the best performance is using the SWIN transformer with the LoRa rank 4 with the smallest rank, giving us the highest performance. And this is mainly because of using rank 4 is less prone to overfitting. So the model can generalize well and learn well the data set it needs. And also for the parameters, we can see that the original SWIN transformer was trained using an 88 million trainable parameters, which is very high. And using the LoRa adapters, we have reduced this to 28 million, which is 68% less. And also for the epoch time, we have reduced this from 4.2 minutes to 2.5 minutes. So what is the significance of this? Basically, it is clinic ready. It can run on affordable GPUs, and it can be used directly to do the classification for the skin cancer dataset, as we said. And also the same LoRa, like the same method or the same backbone with the LoRa adapters can be used for other tasks such as CT, X-rays, and also pathology or other modalities. And it bridges the gap, as I said, between the foundation models, which is the SWIN transformer, and the real world healthcare. So the future outlook for this, it can be that we need to do benchmark. Like LoRa is not the only adapter we have for BEFT or parameter efficient fine tuning. There are some other methods which come after it, such as the adapters methods, the BETFIT methods, and some other methods that we can also test its adaptability to the backbone, such as SWIN transformers or other backbone, and test it with the method we have. And also one thing that will be more good and more close to the real world application is trying to do inference on the smartphones or the on-device or the edge devices inference, how we can get the model to run on not very high GPUs, because it's also not very available at every clinic. So having it running on a smartphone can be a very big advantage. And yeah, the last thing is that we can test it across also multiple datasets, not only the HAMS 1000 dataset, but also across other datasets that we have. So to conclude, as a take home. We have LoRa. LoRa stands for low rank adaptation. It's a very effective and tiny and add very low overhead to be able to tune a transformer or a backbone or a pre-trained model to a specific task. And we have Swin plus LoRa. It gives us the full fine the best results and better than the full fine tuning on the cancer data we have. So thank you. That's it.